Okay, so this should be the last section. I'm going to finish off Kepler's second law, talk about Kepler's third law, and orbital period and how it all relates to gravitation. So before I do, I actually want to show an animation. So as you can see here is, I actually set the eccentricity so we see more of an ellipse, and actually I'm going to make it even more so. I'm making this very dramatic. Although planets are not as dramatic as I'm making them. The point being is, notice how much slower it goes right here. I know we're just going to have to let it go. And watch how much faster it goes over here. And if I start sweeping, and these are all going to be equal time periods, because the program's going to calculate that for us. There we go. So as you can see, this is going faster, so you're going to sweep out more. Well, you're not going to sweep out more, but this looks like it's, more here because you have a smaller spot, but a wider opening, as you can see here. And then all these colored triangles represent the same area. And these all happen in equal times. And this is rated on the animation to do that. So it's pretty neat. So Kepler's first law, if I change this to Earth, this is more of what we'll see. The animation's going real fast, right? There we go. And notice that these are actually more circular. It's not perfectly elliptical, but you can get an idea here. So now we're going to talk about Kepler's third law. Oops, not rotation. So there you go. Here it is again. So I'm going to derive this out. But Kepler showed this through data collection. So what he did was he collected data on orbital period and orbital radius. So T represents the period of how long it takes to make one circle, one revolution around the whole system, and R is the orbital radius. So what Kepler did is he noticed some of these these values. This is data, so this is a period in years, and AU represents astronomical units. So it means the distance from the Earth to the Sun. So notice that's 1 here because 1 AU is the distance from Earth to the Sun. These are closer, so it's less than 1, and these are further because they're further than the Earth to Sun distances. So what he found is he played around with these. He found that the period and the distance, he graphed them. He made a lot of graphs to do that. And he found when he made the graph of T squared and R cubed that he actually got a linear relationship. I don't have the graphs right here, but I can show them in class later. So anyway, you can take my word for it. So Newton was a pretty smart guy. He actually made this completely independent connection as well, which means that, of course, a good science, you can repeat it. So Newton's law of gravitation says G, and we could do it of, sure, the moon. It doesn't have to be. I'm just using a random example here. It could be anything. So Earth, moon. So we said that the gravitational force is causing, the centripetal force. So remember, this is m moon, v squared over r, like that. So what we can do is we can take our v here and write it with orbital period, where t is going to be orbital period. So remember the definition of a period. Period, it means how long it takes to make one complete cycle. So notice that's really appropriate for satellite motion because it's good to know how long it takes to get back to its spot. For example, the orbital period for Earth is 365 days. The orbital period for the Moon is about 27 days. So knowing these values are very helpful for planning and, of course, astronomical predictions. So what I'm going to do is take this and plug it into here. So I'm actually going to simplify it like I did earlier because it just makes the math easier. You can go ahead and plug it in, but you'll see why I'm doing this. because what's going to happen here is I have to square v when I plug this in. So that's going to look like this. So I get this stuff on this side. Oops, sorry, that is not squared. Take that out. Oops, I want to square it. It's not squared. Let me just be very sure that that's true there. Okay. So v, I'll just write it here for reference, is 2 pi r over t. So if I square this, it's all multiplied. So I can just distribute the squared. So 2 times 2 is 4. Pi squared, r squared over t squared. So if you see where we're going with this, I want to solve for t, orbital period. So that's going to come up onto this side, and this will come up. So I'm just going to switch the two. So t squared g me. Oops. And then r is going to go over there equals 4 pi r. They don't cancel, they combine. So that becomes cube. And then solving for t. Like that. So sometimes, and if you notice, I'll leave it in this form first because you can see the relationship that Kepler was doing. T squared, r cubed. Kepler said that t squared is proportional to r cubed, which means they're related. But this is not how to calculate the actual values. To do that, you have to use this equation here. So what I can do is I can find t, and if you notice, I'm going to take the square root of this whole thing because it's squared. Got my squared there, sorry. And then a little mathematical trick. 4 square root is 2, and that pi square rooted is actually just pi. So I can take that out of the radical and leave the rest in here. Now you can write it in each or either of these forms. It doesn't matter. It's your personal preference. You could even keep it like this if you'd like. But this is the orbital period. So some notes about this. Orbital period is measured in seconds. So generally your periods are going to be in days, years, months. So just make sure that this is in seconds. And generally this is a large number. I have it as Earth, but as a general case, this is the central object once again. So central object. And that's measured in kilograms. R is our orbital radius, measured in meters. So once again, you're going to get different units like kilometers and astronomical units. So 1 astronomical unit is roughly, please look this up because I don't want to be, I think it's by memory, it's to the 9th. I think it's something like that. But you know, if you see it in AUs, you have to convert it. But from this, we can find orbital periods of just about anything, such as the orbital period of the moon or the orbital period of the Earth relative to the Sun. They should actually equate to the values that we're familiar with. So this is just a slide with that derivation right there, doing the same thing, talking about it. So Kepler's third law basically relates orbital period to orbital radius, saying that if you're further away, it's going to take longer. And I hope that makes sense to you. And if you're closer, you're going to go faster. And this is exactly what I just kind of described earlier. And this is how we can discover things, such as like the mass of the star. So you can try this exercise on your own, but if you use the equation in the previous slide, you'll find that you could actually calculate things like the mass of the sun. So you can try that out. But notice this is in days, so you have to calculate this into seconds. So you're going to be dealing with really large numbers when you do this. So if you see like 800,000 seconds, that's okay, especially for some of these values like that. So another word you have to be familiar with is the geosynchronous orbit. Geo represents the Earth, and synchronous means the same. So the same orbit as the Earth. That's what this translates to. So a lot of our satellites are a geosynchronous orbit, which means they orbit 24 hours. That's because they want to stay in the same spot as Earth, and since Earth is rotating, they must maintain that same spot. So if you ever see the word geosynchronous, it represents a very specific orbit time. It's 24 hours. So here are the 4 things you need to know. The force of gravity, how to calculate it. Local acceleration, how to calculate the acceleration due to gravity based on the planetary information. The orbital velocity based on planetary information and orbital period. And notice each of these, the biggest things that contribute is the mass of the central object, even though the variables are different, don't worry about that. They both mean the big M here. And sorry, same thing, I can see how this can be confusing. So regardless, it's always the big M refers to the mass of the central object. R refers to the radius, the orbital radius, and I think everything else should hopefully be pretty self-explanatory. These are the highlights of the exam for the most part. And they like to do not so much calculations, but manipulations with these. If I double the mass, that's going to double our acceleration. If I double the radius, that's going to reduce it by 4. So be able to recognize and understand these relationships. So some of the homework questions or some of the multiple choice extra practice problems will help you emphasize that. So all of these describe how things move in space. We use a little bit of circular motion, a little bit of gravitation, and a little bit of force and knowledge to calculate some values here. So that concludes our whole segment on gravitation and satellite motion.